Hello, wonderful people, and thank you for coming to a deep dive into shallow immutability, where we'll explore what's coming to Kotlin, how Project Valhalla ties into all of that, and what it opens up and coming up into the future. My name is Marat, and as this is my first time giving a talk at KotlinConf, a short introduction is in order. I'm currently a researcher at the Kotlin language evolution team under Michael Zarechensky, where I work on all things language design related. If to some of you my name sounds familiar, then thank you, because I assume that is because you read Kotlin language specification, which I worked on previously. And I also did some other things related to Kotlin, Kotlin compiler, analysis, and so on. But the talk is not about me. This talk is actually about new immutability features that are coming to Kotlin, mainly in two forms. First, in the form of deeply immutable value classes with multiple properties that are checked and enforced by the compiler. So now you can have not only limited inline value classes with only one property, but actually, you can have multiple properties, and it will give you not only shallow, but deep immutability. And I'll be talking about that going forward. And also, we'll be giving you a thing which is called copy vars, and I explain what those things are in the talk. They are a way to ergonomically update immutable data, because despite data being immutable, still programs often have to mutate that immutable data, and we'll give you ergonomic ways to do that. This talk, however, is not about how immutable data helps you in your architecture or in your design. If you want to know about that more, then I highly recommend going and watching a talk, Good Old Data by Andrei Zaitsev, which is very conveniently right after my talk in Auditorium 11 and 12. And this talk is also not going to be talking about other more complicated aspects of immutability that go beyond the scope of what we're currently planning to do in Kotlin. And immutability is a very complex subject. It has a lot of things, a lot of interconnected parts. Some might say that it's as complicated as Marvel Cinematic Universe, and I have it on good authority that there is actually a Marvel Immutability universe where all the superheroes are worried about is immutability. And today we're going to go on a short trip in this Immutability universe, exploring what actually it means. So first, we're going to take a look at an old classic. We're going to take a look at Avengers Immutability Wars, which came out in 2011 in that universe. And we're going to focus on three main questions. What is immutability? Where is immutability? And I'll do you one better. Why is immutability? Why we care about it? So let's go one step at a time. So what is immutability? A very broad definition is immutability is when something in your program cannot be changed. I'm not happy, coming from a scientific background, I'm not happy with this very vague definition. As you can see on the slides, Cody is also not happy, and probably many of you are also not happy with the definition. So let's try to narrow it down a bit. Let's try to explain it a bit. So immutability is when something cannot be changed, and these two axes, what something is and what does it mean it cannot be changed, are important. So let's focus on the first thing first. So something is actually anything. It could be a property of your data class. If you declare it as a val, then it means that it cannot be reassigned, it cannot be changed, it is immutable. This property, its reference is immutable. It can be a collection in the standard library with some terms and conditions applied. So for example, if you have a read-only list and you know that there are nobody who's trying to cast it to a mutable list and change it, then you know that you just cannot do this because there is no API, there is no add method they could change this collection. Well, actually, as I just said, it can be anything. Any entity in your programming language can be viewed as immutable if your language or the developer wants to view it as immutable. It can be an interface. You can say that this interface is immutable, it cannot change in state. You can say that a type parameter is immutable, a property, an anonymous object literal, whatever you want. And the main distinctions here are what actually you want to say is or isn't immutable, and whether the control for immutability comes manually by a developer being great and not making any mistakes, or automatically by a compiler being there for you and helping you to enforce the proper use of immutable things. What does cannot be changed then means? Well, actually, again, there can be one of two things. First, you can work with what is known as concrete state, or air quotes, physical state. So like your bits and bytes, the actual raw underlying representation of your object, it cannot be changed. And no matter how you view this state, no matter what API surface you open up to your raw bits and bytes, it doesn't matter. The bytes themselves cannot change. That means that no matter how you observe them, how you view them, the results of that, they cannot be changed. An example of this is like a raw byte array that you froze and you said that it's immutable. Java long string is a great example of that, because the underlying bits and bytes of your Java long string, they are immutable since Java, I don't remember when they changed that. But basically, you get the point. Alternatively, what you can say is you can say that actually, I just have an opaque box. Internally, I don't care what it is, but the way I view this thing from the outside, its abstract state, as it's also known, this thing cannot change. And the thing is that your underlying state can actually change. For example, if you have a skip list or a splay tree, internally it can rebalance itself, but if you say that it's immutable, you cannot add new things to it, then externally, from the outside observer perspective, this thing is immutable for all intents and purposes. So why are we talking about this? Why this distinction is important? This distinction is important because reasoning automatically by the compiler about the concrete state is way easier than reasoning about abstract state, and it will become important a bit later. So now we understand that immutability is when something, you decide what that something is in your language, cannot be changed either as a concrete state or as an abstract state. Let's take a look at any already existing things in Kotlin that support immutability. And there are. Kotlin supports simple, pragmatic immutability, heavily inspired by multiple different things. For example, by Effective Java item 17, which greatly talks about immutability and why it is important. It goes about it a little bit at the other end. It says minimize immutability, which means embrace immutability. And it has a bunch of advice for you as an application developer on why you should care about things being immutable rather than mutable. And Kotlin has you covered. So Kotlin adheres to, like, if you want to avoid providing mutators, we have a very convenient syntax for that. You just make things as vals, and we actually advise you in our documentation to preferably use vals because they make it so that your data is immutable, and that's better for your application. Some things are just not expressible in Kotlin. Effective Java says make all fields private. In Kotlin, there are no user visible, developer visible fields, so that source of possible mutability is not even a problem in Kotlin because there is none. And we'll also give you additional good ways to, for example, solve the ensure exclusive access to any mutable components by giving you ways of projecting collections to their read-only views, or to giving you convenient ways of copying mutable collections defensively into their immutable siblings. So like, we have a lot of checkboxes covered in Effective Java item 17, but we'll be covering more. And now I want to talk about why we actually want to cover more. So an easy answer would be, well, item 17 already says that I should care about that. Let's just care about that, and that's it. But I'm going to go a bit beyond, and I'm going to try to convince you with several examples of what actually happens in actual development, why immutability is important there. So I'm going to be talking about how UI programming greatly benefits from having immutable data, and I'm going to be talking about how caching also prefers you to working with immutable data rather than immutable one. So UI programming. As most of you probably know, like, we've come a long way from like way old monolithic UIs where everything is super interconnected and like it's spaghetti code of your state and your updates and the way the UI renders on the screen all mixed up together. Then we understood it's not manageable. We evolved into having some separation, some architecture, for example, model view controllers and other 3-4-letter abbreviations. And currently we have these reactive UIs, for example, Jetpack Compose, which very informally, don't quote me on that, but very informally, they take the C out of the MVC model and they automatically bind updates of the views with the moments when your models actually actually change. What it means? It means that the framework needs to understand when your models, when your data actually changed. That means that you have to track the state changes. And it looks like a simple problem, right? Well, actually, and I guess a lot of you already know about what I'm going to be talking about, this is not that easy. Like Compose uses this term stability, which is another way of saying it is immutable or I know how to track it. And like, let's say we have this super simple example of a composable, and somewhere deep in this composable, we have a contact, and we want to understand, do I need to recompose this UI? And I, for some reason, decided to shape the API of the contact the way it's presented on the slide. If you take a look under the hood, if you take a look at the stability reports of the Compose compiler, then you will see that it tells you, well, actually, because you have a bunch of vars, I don't know if this thing is stable. I don't know if it's immutable. And I will be very pessimistic about the update. Because tracking changes in mutable data is hard. How we can make the Compose compiler happy? Well, if we actually by ourselves, knowing about this problem, if we change the data shape to have only vals and be deeply immutable, then Compose compiler says that, well, now I know that everything is definitely deeply immutable. I can easily track the changes. I can understand when the data changed or didn't change, when I need to recompose or I don't need to recompose, and I'm happy. But you have to do this manually. And it's a known best practice. So immutability is approved by Compose. It encourages you to work with immutable data, make your domain models immutable, if you can do this. So let's go to caching. Caching is, if you take a very close look at it, in some sense, very similar to UI programming. It's, again, you have some inputs, your state of your UI or just some inputs to your computation, and you get some results. Whereas the difference is, whereas in UI, your output is the drawn UI, with caching, your output is, again, some data that you want to work around with the program going forward. And that is another point where you also care about immutability. So Compose cares about the immutability of the inputs. Caching, additionally to that, cares about immutability of the outputs. Why? Well, because let's have, again, an example from some enterprise system that tracks books in a school library or whatever. And somebody wrote a library repository that allows you to get books. They tried to be immutable about it. They were smart enough to return a mutable list, but the data class book was outside their control, and it is immutable. And some client of this repository was a bit egoistic. He decided that the capitalization of the books is wrong, I need to fix it, and they just updated it in place mutably. And what happens after that is, without you understanding that, what happened, because it happened in somebody else's code, your cache is now invalid. They corrupted the state of the library repository by updating this mutably in place. How do you avoid this? Well, again, by being a great developer, remembering about this being a possibility, and remembering to make your book immutable. And in that case, the egoistic client cannot be written anymore. They have to make a copy. They have to update all the books independently from the cached version, and then the cache is happy. So caching also cares about immutability of the outputs. In some sense, immutability is also approved by caching, and approved even more because it cares about inputs and the outputs. So what do we need? We need some kind of better immutability because Compose needs it, caching needs it, a lot of other examples also need this. And we're in this situation, we're in front of a rift where we have simple pragmatic immutability on one side, and we want to get to this world with better immutability on the other side. How do we do this? How do we do this? So we do this by taking a look at what's going to be coming as Project Valhalla in 2020-something. We don't have a release date for this movie yet. And we're going to be talking about what is actually missing, what's coming to Kotlin, and how does Project Valhalla, that I talked about in the title in the very beginning, ties into all of this. So what is actually missing? Let's try to understand that. Again, going back to the definition of immutability, we need to understand what is that something that we want to make immutable to make Compose, caching, and other use cases happy. We already have immutable references, which are enforced by the compiler, but we do not have yet any notion of immutable values that are checked and enforced by the compiler. So we neither can control this on a fine-grained level by saying that an actual concrete instance is immutable, nor we have a notion of immutable types. And that's basically what we need to add to the language. We need to have a notion of an immutable type that is enforced by the compiler. Now let's pretend that we just have some special kind of data classes that are forced to be immutable. What restrictions do they have? Restrictions are relatively simple. If you care about shallow immutability, then your stored concrete properties, they should be vals, and you can write this even now. If you want to care about deep immutability, then basically you want transitive shallow immutability. All of the properties are vals, and also their types themselves are also deeply immutable. And if we stop here and think for a second, why do we talk about concrete properties, about concrete state? Going back again, that's because the compiler will be able to check the concrete state automatically, whether you violated or not the immutability properties. And are we happy with just being, extending data classes to have immutable data classes, if you will? Well, almost, but there is one important thing that we have to get rid of to be truly happy. The thing is that concrete state doesn't go well with identity, and data classes have identity. Why identity is bad for the concrete state and for immutability in general? Because identity, because you understand what is the box in which your data is actually stored, this box is inherently mutable. You cannot just strip immutability from this box, and that is something that we actually do not want. So, what is missing? We want to declare deeply immutable types that are checked and enforced by the compiler, basically using vals or vals of immutable types or transitive vals of immutable types. And they should not rely on identity. If we put 2 and 2 together, that means that we need better value types. And that's exactly what's coming to Kotlin. Important note, everything that I'm going to talk about is work in progress. Some of the design may change, some of the modifiers can change, but overall, the global shape of the design is going to stay the way that I'm going to be talking right now. So right now, we already have inline value classes, which are shallow immutable types with a bunch of additional restrictions. They don't have identity, which is great. We love that. We want that. All of their properties are vals. Again, that's great. That's what we wanted. But they only allow one stored property, and that's problematic because we want to be able to work with complex data, composite data. And they only support and enforce shallow immutability. Important, as most of you probably know, they also inlined whenever possible, but first and foremost, the inlining of value classes is an optimization. It's not integral to the immutability part of the story. So let's try to leave these restrictions, and this is the first thing that's coming to Kotlin. We are introducing immutable value types with multiple properties. So we're basically lifting the restrictions of inline value classes that stop us from having proper immutability that like compose, caching, and other cases benefit from. So you can have more than one value in your value class once this rolls out. If you care about deep immutability, you will be able to mark your value class as immutable to make it deeply immutable, and that will be checked by the compiler. Other restrictions will be mostly the same as for inline value classes. So for example, it must have a primary constructor. All of the actual properties should be declared only as primary properties in the primary constructor, and so on and so forth. What is important to note here? They will be not inlined right now, because inlining is first and foremost an optimization. It's not, again, integral to the immutability part of the story. Whether and when we can solve this performance problem, I'll talk a bit later. So is this everything that we need to be happy? Well, once you begin pulling the thread, the story becomes more and more and more complex. So thing number one, deeply immutable value types we want them, but they actually need more support than just saying that, well, now you have immutable value classes. Why? Because for value types, we know about deep immutability or no deep immutability. Regular value classes are shallow immutable, immutable value classes are deep immutable. Within the value world, everything is okay, but we have this huge, wide reference world that's already there, for which we have no idea whether reference types are deeply immutable or not. So, for example, list. We have no idea whether list is mutable or immutable. What you can do is you can do what Compose, again, advises you to do. You can know that, well, immutable list is immutable. It adheres to immutability principles, and you can just say that, well, here I'm just gonna, again, rely on Kotlin developers being the best developers there is and not making mistakes and remembering to always use the correct reference types when they're working with immutable value classes. But we can do more, and what we'll actually do, and that's the second thing that's coming, is we're going to give you a way to say as a contract that this reference type is definitely immutable. You can safely use it within your deeply immutable value classes, and it's completely safe to do so. For example, we're going to be marking immutable list, immutable set, and all of the other immutable collections from Kotlin X collections immutable as add immutable to kind of like bridge these two worlds together, to connect value classes with reference types, reference classes that are known to be deeply immutable. Important, this will be a contract, so if you made a mistake and you marked something as immutable when it's actually mutable and somebody can mutate it by mistake, you might have problems, the same problems as we discussed in the very beginning of the talk. So if we continue to unroll this, it becomes even more interesting. So immutable list is generic. And if you, again, take a look at this thing, you will realize that the deep immutability of your immutable list is conditional. It's conditional on what's the actual type parameter for your immutable list. If you have an immutable list of deeply immutable contact, it's say, OK, the whole thing is deeply immutable, you are happy. If you, for some reason, decided to create a mutable list of int, or you decided to wrap a mutable list inside your state or your mutable state, then you have a problem. And that's the third thing that we're giving you. We'll be giving you a way to mark generics for which you want to ensure that they're instantiated only with immutable things as immutable. And this will be, again, checked by the compiler so that you cannot accidentally make a mistake and pass an immutable a mutable thing to some place where it actually expects an immutable type. So this is, in aggregate, the first thing that's coming, an extension of current value types in Kotlin, which are support multiple properties and which are support also deep immutability, which is checked and enforced by the compiler. Is this everything that we'll be giving you? No. The second important part of the story is as follows. In the old immutable world, if you want to update your immutable data, and immutable data currently is very often represented as data classes, you do a bunch of copies. Looks innocent enough, right? Well, yes and no, because as a lot of people probably encountered, if you need to update some very deeply nested immutable structures, then you run into a thing which I like to call the copy ladder, because it kind of like goes way past your character limit of 80 characters or 120, or depending on the size of your screen. Like it very fast goes almost uncontrollably. And that's not what you actually want. You actually want to take the elevator, because like that's what you want to express. You want to express, I want to update a bunch of things in this data structure. The compiler, or whoever the hell is, they should be able to understand what needs to be updated and how it needs to be updated to actually reconstruct the resulting data structure. And actually, maybe we can try to nudge Kotlin compiler into being smart enough and kind of like taking the ladder instead of us, so we kind of like shortcut it in a way, and there are actually several ways you can achieve this. The way that we're looking at, and I won't go into the technical details of, we're piggyback riding on a thing which is called mutable value semantics, and we're taking a light version of it. What it basically means is that if you mark and you say that I'm opting into mutable value semantics, I'm saying that there is a copyvar fixed book, and on it I can update it and something magical happens under the hood, I'm okay. What actually is this magical copyvar thing that's happening under the hood? You can mark your properties of your value class as copyvars, and then you can opt in on the reference of such a value class as a copyvar, and then you can just write your very mutable, imperative-looking code. You can just take the elevator. You write this, and you don't care what actually happens under the hood, because that is taken care of by the compiler. And what the compiler does, the compiler is smart enough to understand that this is the value class structure that we have. And it knows it because, again, we took care of having only concrete state in our value classes. And it knows that, well, I can actually reconstruct everything from this. I know that the person wants to update the title, and it wants to update the EN prefix inside the ISBN. I can automatically, under the hood, compile it into code, which will do everything without the user needing to type out these copies or with titles or whatever. How exactly it's going to be compiled down to, that is something we're thinking about. For now, we're heavily leaning towards what's on the slide, which is basically something very similar to the wither convention that you usually have in Java. Because, for example, it gives us the opportunity to optimize extra allocations if we see a chain of these withers. The Kotlin compiler take a look at the code here, and it can see that, well, actually, the updated book with title doesn't leak anywhere. It's immediately reassigned again. I can just automatically collapse it into this with aggregate and avoid the extra intermediate allocation. This is something that we'll be working on. It might come a bit later. If you don't have that, then you have the same allocation pressure as you would have right now if this were written with data classes. Once we have this possibility of optimizations, and once we have this with aggregate convention narrowed down and designed, then you will get less allocations that you would have otherwise. So that's the second thing that you're getting. You're getting a way to say that I want to ergonomically update my immutable data. I want the compiler to figure out how to rebuild this data by obtaining into this thing which is called copyvars. And copyvars allow you to do more things. For example, if you want to bunch up several updates together into a function, what would be a way to do this right now? Well, you can just say that let's do it Fluent style. Let's say that I want to normalize the book like this. And I will just reassign it. And book normalize says, well, actually, the self here is a copyvar. I'm going to write a bunch of boilerplate. I'm going to say that copyvar self is this. Then I will assign a bunch of properties, and then I will return it. But we can try to take the boilerplate again away and just say that, well, actually, it just means that I need some way to say that within a function, my this is a copyvar, and that's actually a copyfun. And that's an extension of the copyvar idea lifted to functions. And that avoids the boilerplate of needing to return something, to separately declare copyvar self. We just, again, take care from that under the hood. You write normal-looking code that does what exactly it should do, taking a look at how it's written. And we, under the hood, again, compile it down to what you actually meant to say when you wrote this code. There is a lot of other things that we're still actively designing. For example, do we need value interfaces, how we should bridge or not bridge with immutable value arrays, do we need copy functional types, and so on and so forth. It's all a work in progress. In the end, I'll tell you how you can leave feedback on everything. So what about Project Valhalla? Because it's in the air, if you will. Well, Project Valhalla, for those of you who somehow skipped it, but it's like 10 years in the making, it's JEP 401, which talks about introducing value classes on the JVM platform, but for a little bit different goals than ours. The two main goals of Project Valhalla are: first, provide types which opt out of identity, and second, support the opportunity to get nice runtime optimizations of these types which opted out of identity. And if you take a look at how Valhalla value classes look like, they look something like this. Like, once Valhalla comes out, you will be able in your Java code to say that I have a record, it's actually a value record, it brings some restrictions, but it avoids identity, and it will be optimized at runtime. And if you squint real hard, and if you take a look at this thing, basically, JEP 401 value classes are shallow immutable types. So they are a great basic building block for everything that I talked about right now. So as usual, we're synergistic with Java. We're taking the great foundation of the JVM platform, and we're building on top of it. We're adding to this thing control of deep immutability, which Valhalla is not talking about. We're giving you ways to do ergonomic updates of your immutable data, which again is outside the scope of Project Valhalla proposal. And we'll give you better support across other language features. Some of them I will be talking about in the end of the talk. Again, this is about immutability, and we mainly care about immutability. That's why, as I said, when I began talking about deeply immutable value classes in Kotlin, we will not be optimizing them in any shape or form from the very beginning. Why? Because it's about immutability. And if we just wait patiently until Project Valhalla comes out, we will get all of the runtime optimizations built into the JVM platform basically for free. Once we get everything about immutability right and we have spare capacity, then we maybe can think about rolling out our own optimizations before Project Valhalla comes out. But currently, we believe that the immutability part of the story for value classes is much more important than the performance optimization side of the value classes. If you disagree on that, again, please reach out. We're very much interested in hearing your stories and your use cases of why you think that is more important than immutability. So I would like to now to talk about what actually opens up once we have immutability in Kotlin. And for that, this is the Infinity Saga, which is going to release, I have no idea when. A small callback, I cannot avoid it, to my Kotlin language specification writing days. I ask you a very simple question. You can just answer it in your minds after I ask it. So many times do you think immutability as a concept, as a term, as a word, is mentioned in the Kotlin language specification right now? Is it never? Is it 10 times? Is it more than 25 times? So you think very fast, so 3, 2, 1, it's 10 times. And what is interesting is that 8 of those 10 times, immutability is mentioned with smart casts, because smart casts are actually allowed to be safely performed only on things which are immutable. Because if a thing is mutable, then the smart cast might become invalid by the point when you actually perform the smart cast, and that's unsafe. An example of this is your favorite data class pair from the standard library. I wrote several times code like this, and I was very unhappy that the Kotlin compiler is not smart enough to understand that, listen, I checked this data class, that the first is not null. You should be able to append nullable thing as if it's not nullable. But pair comes from another module, and we're very pessimistic. Because we want to be very safe. And for things coming from other modules, we do not support SmartCast for this type. But if you say that pair now becomes a value class, it brings more guarantees from the pair side of things. It means that pair is actually truly immutable. Nobody can change it. This is something that we can actually rely on. And because value types cannot be changed concurrently, and that's That's a kind of a contract. And it means that we will be able to propagate the smartcast knowledge in more cases, so you will be getting more smartcasts if you are using immutable value classes more in your programs. Another thing is how immutability plays with concurrency. If we go back to effective Java item 17, then one of the points is immutable objects are inherently thread safe. And that is totally true. If you have your good old mutable example with your state that you can concurrently change from several different threads, having your favorite data race, that's bad. But let's naively try to change it into using the features that I've been talking about today as in immutable value classes, and let's have a copy var. Let's try to do exactly the same pattern of the code. Is everything okay? Well, actually no, because copy var reference is kind of like a box that you can concurrently change from several different threads. And we want to be able to give you, again, good diagnostics and to help you avoid these kinds of mistakes. And once we get this experience of how value types interplay with concurrency right, we will be probably giving you something like on the slide, a diagnostic that tells you, well, the first capture of state is OK, but the second capture is actually concurrent with the previous one, and you should do something about it. For example, copy the state inside your concurrently executing domain, and then propagate the change back once you're done updating it. Because like, if you have a val reference to immutable data, it's always safe to share. A copy var reference to immutable data is sometimes safe to share if you know that it's definitely not concurrently updated. And if you have a reference to immutable data, your reference-based types or whatever, it's safe to share them if they say that they're thread safe. They were designed with concurrency in mind. The exact rules and what are we going to be doing here, they are yet to be designed. But we hope that that's one of the many things that adding better immutability to Kotlin will give you. So to recap what I just talked about, we will be introducing to Kotlin deeply immutable value types with multiple properties checked and enforced by the compiler, so that you can represent your immutable data that frameworks like Compose can reliably use to understand what has and hasn't been updated, and to avoid problems such as cache invalidations, and so on and so forth. We will be giving you copy vars and copy funds for ergonomic updates of immutable data, so that you can keep writing code which looks nice, which represents what exactly you want to do, while the compiler takes care of all the boilerplate behind of reconstructing the immutable data structure for you. That will, in turn, open up possibility to have better smartcasts, safer concurrency, a lot of other things. And everything is covered currently within KT 77734. That's an issue in our issue tracker, which has a short summary of what I just talked about today. A proper keep will be coming later this year. But for now, if you have opinions, if you disagree with something, if you think that what I said is complete bullshit and it shouldn't come to Kotlin or it should come in some other way, feel free to go there and leave your opinion. It is very important to us. Because if we don't hear from you, we are unfortunately not yet telepaths. We cannot read your minds. We don't know what you actually want. With this, that is all from me. Thank you so much. Don't forget to go to the issue, and don't forget to vote for the talk if you liked it. Thank you so much.